Hi friends, today we study vibration of air column in a pipe open at both ends. Okay. आता आपण काय स्टडी करणार आहे आज the vibrations of air column in a pipe open at both ends. Okay. In this case, boundary conditions are such that an antinode is present at each open end. When a source of sound, like a tuning fork, is held near one end of the pipe, it sends the waves inside the pipe. Okay? म्हणजे याच्यात आपण काय करणार आहे? एक पाईप घेणार आहे ज्याचे दोन्ही एंड काय असणार आहे? ओपन असणार आहे. ट्युनिंग फोर्क घेणार आहे. ट्युनिंग फोर्क हॅमर केल्यानंतर त्याच्यावर एक्झॅक्टली जवळ राहणार आहे. ओके? जेणेकरून तुमच्या त्या वेव्स ह्या पाईप मध्ये सेंड होणार आहे. ओके? Even though both the ends of the pipe are open, the air inside the pipe is still bound by the wall of the tube. As a result, the air inside the pipe is little denser than the air outside. When the waves travel to the other open end, there is partial reflection at the open end. The partially reflected waves superimpose with the incident waves. Under suitable conditions, stationary waves will be formed. There is maximum freedom for motion of air column at both the ends, as pipe is open at the both ends. Suppose a compression produced by a tuning fork travel through the air column, it gets reflected as rarefaction at open ends. The rarefaction moves back and gets reflected as compression at the other end. It suffers second reflection at open end near the source and interfere with the waves coming in by a path difference of twice L. The different mode of vibration of air column in pipe open at both ends are shown in figure A, B, C. See figure A, B, C. Okay. The fundamental tone or mode of vibrations of air column open at both ends as shown in figure A. There are two antinodes at open ends and one node between them. Length of air column for this is capital L is equal to lambda by 2, and here we get the lambda is equal to twice L. Okay, same here use the relation between the frequency, velocity and wavelength. Then here we get the frequency n is equal to v upon lambda. So is equal to v upon twice L. Put out the L is the L plus twice E because both ends are open. So here capital L is equal to small l plus twice E. Okay, then here we get the V is equal to twice N L. This is the fundamental frequency or the first harmonic. It is the lowest frequency of vibrations. See this figure. Both are antinodes and in this between one is the node. And distance between the air column is equal to the lambda by 2. Then see here. There are two nodes and 3 antinodes. In this diagram, 4 antinode and 3 nodes. Distance is the 3 lambda 2 by 2. Okay, see here. First we see the first diagram. In first diagram, we get V is equal to twice NL. Okay. In second diagram, means the next possible mode of vibration of air column open at both ends is shown in figure B. 3 antinodes and 2 nodes are formed. So length of air column is equal to the capital L is equal to lambda 1. That is lambda 1 is equal to capital L is equal to L plus twice E. If N1 and lambda 1 are frequency and wavelength of this mode of vibration of air column respectively, then the V is equal to N1 lambda 1. From this we can find the N1. So N1 is equal to V upon lambda 1 is equal to V upon L. So then we get the V upon L plus twice E. Means here we get the frequency N1 is equal to twice N. This is the frequency of second harmonic or first overtone. In the next vibration of air column open at both ends as shown in figure, there are 4 antinodes and 3 nodes are formed. So length of air column is the 3 lambda 2 by 2. Okay. So here we get the lambda 2 is equal to twice L upon 3 is equal to twice L plus twice E upon 3. If N2 and lambda 2 are the frequency and wavelength of these modes of vibrations of air column respectively, then V is equal to N2 lambda 2. Put out the value of lambda 2. Okay. So here we get the frequency N2 is equal to V upon lambda 2 is equal to 3V upon twice L. Then we get the 3V upon twice L plus twice E. That is the N1 is equal to 3N. This is the frequency of third harmonic or second overtone. Thus all harmonic are present as overtones in this mode of vibration of air column open at both ends. Okay. Then next, प्रॅक्टिकल डिटर्मिनेशन ऑफ एंड करेक्शन. आता आपल्याला काय काढायचंय, एंड करेक्शनचा फॉर्म्युला काढायचा आहे. एक्झॅक्ट मेथड टू डिटरमाइन द एंड करेक्शन युजिंग 2 पाइप्स ऑफ सेम डायमीटर बट डिफरंट लेंथ L1 अँड L2. ओके. म्हणजे आपल्याला सेम पाईप घ्यायचा आहे ज्याचा डायमीटर काय असणार आहे, सेम असणार आहे. ओके. फॉर अ पाईप ओपन ॲट बोथ एंड्स V is equal to twice N1 L1 is equal to twice N2 L2. Okay. Then here we get the N1 L1 is equal to N2 L2. Okay. Put out the value of L1 and L2 for the open end. Okay. So N1 into L1 plus twice E is equal to N2 L2 plus twice E. Okay. Write down the formula for E. So E is equal to N1 L1 minus N2 L2 upon twice N2 minus N1, or N2 L2 minus N1 L1 upon twice N1 minus N2, bracket complete. Okay. This is the formula for the pipe open at both ends. Next, for a pipe close at one end. So same here, V is equal to 4 N1 L1 is equal to 4 N2 L2. Okay. Then here 4 get cancelled, we get the N1 L1 is equal to N2 L2. Okay. So N1 into L1 plus E is equal to N2 L2 plus E. Here we get the E is equal to N1 L1 minus N2 L2 upon twice N2 minus N1. Same here, E is equal to N2 L2 minus N1 L1 upon twice N1 minus N2. Here we get the end correction formula. Okay. Then next, we study the vibration produced in a string. Okay. So consider a string of length L stretched between 2 rigid supports. The linear density is small m and tension capital T. Act on a string due to stretching. If it is made to vibrate by plucking or by using a vibrator like a tuning fork, a transverse waves can be produced along the string. When the waves reaches to the fixed end of the string, it gets reflected with change of phase by pi radians. The reflected waves interfere with the incident waves and stationary waves are formed along the string. The string vibrates with different mode of vibration. If a string is stretched between 2 rigid supports, and is plugged at its center. The string vibrates as shown in figure A. It consists of an antinode formed at the center and nodes at the two ends with the one loop formed along its length. It is the wavelength and L is the length of string. Then we get the length of loop is equal to lambda by 2. So here get lambda is equal to twice L. The frequency of vibration of this string is given by n is equal to V upon lambda. Put out the value of lambda. Okay. And V is under root T upon M. T is the tension, M is the mass per unit length, linear density. Okay. So put out the value of V and lambda. 1 upon twice L under root T upon M. This is the lowest frequency with which the string can vibrate. It is the fundamental frequency of vibration or the first harmonic. Then, if the center of string is prevented from vibrating by touching it with a light object and the string is plugged at a point midway between one of the segments, the string vibrates as shown in figure B. Two loops are formed in the mode of vibration. There is node at the center of the string and at the both ends. If lambda 1 is the wavelength of vibration, then the length of loop is the lambda 1 by 2. That is the L by 2. Lambda 1 is the length L. Thus the frequency of vibration is given as N1 is equal to 1 upon lambda 1 and into under root T upon M is equal to 1 upon L into under root T upon M. Thus the frequency of the first overtone or second harmonic is equal to twice the fundamental frequency. Then next, the string is made to vibrate in such a way that three loops are formed along the string as shown in figure C. If lambda 2 is the wavelength, here the length of one loop is lambda 2 by 2 is equal to L by 3 under root T upon M. So here we get the lambda 2 is equal to twice L by 3 into under root T upon M. Therefore, the frequency of vibration is N2 is equal to 1 upon lambda 2 is equal to 3 upon twice L. Compare with fundamental frequency, then we get the N2 is equal to thrice N. Okay, thus the frequency of second overtone or third harmonic is equal to thrice the fundamental frequency. Similarly, for higher modes of vibration of the string, the frequency of vibration are as 4n, 5n, 6n, etc. Okay, thus all harmonic are present in case of a straight string and the frequency is given as Np is equal to Pn, the fundamental frequency of a vibrating string, and the tension is given as N is equal to 1 upon twice L. 1 upon twice L. Into under root T upon M.